Thank you, Mr. Chairman. As mentioned, my name is Utela. I'm from Vaisala. My responsibility at Vaisala is the weather radars, all the weather radars we produce at Vaisala and related products. So thank you for this opportunity to give this talk, and unfortunately it's going to be in English. My Italian vocabulary is approximately 2 words, so please bear with me. So I will attempt to share my view of how things are developing, or what is the current practice in weather radar transmitters, and perhaps what is the future. It's going to be my view, so I will be happy to discuss how you see the situation. So basically, to start from the beginning, what is the job of the weather radar transmitter? Like in all radars, the transmitter needs to generate powerful pulses of microwaves. It's simple to say like this, but as they say in English, the devil is in the details. So there's quite a lot of additional requirements about the stability of the pulses, power, frequency, phase, and many other conditions. I will mention many of them later in the presentation. So basically, it's a fairly demanding part of the weather radar as well. And in fact, it's one of the most expensive parts of the weather radar. It plays an essential role also in the performance of the weather radar, and it tends to be maintenance intensive as well, at least the traditional technologies. So how are transmitters typically defined or specified? Well, the parameters we often see specified are, of course, the pulse length, the different lengths available from the transmitter, pulse repetition frequency, how often we can send these pulses, and certainly transmitter power, because it's related to the sensitivity of a weather radar. And a weather radar, typically with a weather radar we want to measure at long distances, so it is important to have enough sensitivity. So we often see that the transmitter power is defined or specified as peak power of the transmitter. But perhaps it would be worth considering actually the average power of the transmitter, which is then a function of peak power, pulse length, and pulse repetition frequency. So it's a bit more complex in that sense, and typically the maximum duty cycle of the transmitter is then limiting this average power, at least with the traditional devices. So there's quite a lot of parameters, and they kind of play all together, or are depending on each other, and depending on how the radar is configured to measure. So it's not trivial to specify the transmitter actually. Finally, one important measure is as well the phase noise, which is related to the coherency, pulse quality of the transmitted pulses, and it gives a certain measure of the measurement quality of the radar. Phase noise isn't actually fully dependent on the transmitter only, it's kind of a system parameter actually. But transmitter has a key role in that as well. Other important considerations, of course, is the longevity of the transmitter. How long it will last. Cost, certainly. Then I've mentioned spectrum compliance, meaning that for device transmitting radio waves you need a permission to transmit, and there are certain criteria for that. Typically the local authority sets certain limits, or how much spectrum is allocated to the radar and how much spurious it is allowed to transmit. And finally, of course, the maintainability of the transmitter is a key factor. You want to keep the radar running for years and years. So before I get deeper into the technologies, I want to introduce this concept. There's basically 2 different ways of generating high power microwaves. Either you have an oscillator that by itself produces very high power pulses, or you have a precise low power oscillator and then a very high power amplifier. With this latter technique, the waveform can be controlled much better. You can apply certain coding, for instance, And you can actually combine outputs of several amplifiers, put them in parallel if the amplifiers are high enough quality. So then going into the more traditional devices used in radar transmitters. They belong to a family of devices called vacuum electron devices. So basically devices which have 2 or more electrodes in vacuum and with high enough voltage between the electrodes, you can get electrons flowing, electric current flowing in the vacuum. And in most of these devices, you need to have heating to stimulate the emission of electrons. Why I'm mentioning heating, the reason is that if you think about traditional light bulbs, which were based on heating a metal coil, they don't last forever. So the same thing applies for these devices. The heating coil doesn't last forever. So there's a limit to the lifetime. In radar transmitters, weather radar transmitters, the devices we typically use require pretty high voltages, tens of kilovolts, quite scary voltages, and they tend to generate quite a lot of waste heat as well that we need to deal with. And thinking about this kind of devices, manufacturing and designing this kind of devices requires quite a lot of special competencies. Electromagnetics, high temperature mechanical design, high vacuum, magnetics, and so on. Quite a lot of special competencies, which is fine if you're producing enough volumes of this, then you can maintain all the necessary competencies. But how is future? That's the question maybe. So first of all, the more common of devices belonging in this category is magnetron. Originally invented in the 1930s roughly. There were several different versions of magnetron at that time, but the first good quality or reasonable quality cavity magnetrons were then invented around the Second World War. And the magnetron is a high power oscillator. So it's a fairly simple device in the sense there's the heated cathode and this is the anode. You just switch the voltage on between the electrodes and the tube starts, the magnetron starts to oscillate and you get the high power pulse out. Then you switch the power off and that's the end of the pulse. So it sounds pretty simple, but it's not quite as simple to drive actually. And what happens is that the oscillation never starts exactly the same way. So the phase is random, there may be short timing differences even, how quickly the oscillation really ramps up to the high power. So it's not coherent at all, but what we can do is we can use so-called coherent or receive technique, which means that we sample the output pulse and then correlate the received pulses to the sampled transmitted pulse. Then we can get better measurement performance out of this kind of device as well. The output frequency is determined mainly by the physical size of the physical dimensions of the magnetron. You can tune it by tuning it mechanically, some size of an internal cavity, and thermal expansion will actually cause frequency drift. So magnetrons always exhibit some drift. Klystron is the other fairly popular device in weather radars, invented by brothers Varian in 1937. And the klystron tube is an amplifier. So you have an electron gun and you modulate the drift of electrons, the speed of electrons with a small signal, and from the output cavity you get a high power version of the signal that you fed into the tube. It's an amplifier, so you can get good coherence, low phase noise. There's no drifting frequency if your signal source doesn't drift, which is a pretty easy thing to do nowadays. So what is the downside? Oh, I almost forgot. Typically with klystrons you can also produce longer pulses and have a higher duty cycle. So with the same peak power you can get actually better performance with klystrons. Better coherency, better sensitivity. So the only downside really is that they are clearly more expensive. Much more expensive. So here is from Vaisala weather radar, a klystron version. So our magnetron radar uses one cabinet here on the side. For a klystron radar we need a second cabinet just for the klystron part. And the klystron needs a very powerful electromagnet here to focus the electron beam and a big tank of oil to get rid of the waste heat. So additional complexity is bigger, more expensive device. So magnetrons and klystrons used in weather radars there's quite a good range of devices available with different peak power levels in the X-band, from few kilowatts to then some megawatts in S-band radars. And the way these transmitters are typically used in dual polarization radars is that you have this one expensive device, you generate the powerful pulses, and then you split the power into two equal parts and transmit them in these two different polarizations, horizontal and vertical. So this is how typically they are used. Pulse lengths in the order of microseconds, and the duty cycle we typically get is quite small. With magnetrons, a sort of standard value is 1 per mil. So in every second you can, at a maximum, you can get 1 millisecond of output. Not consecutively, but in short pulses. Klystrons typically achieve something like 2 per mil or even more. And as I already mentioned, these devices have limited lifetimes and they need to be replaced when the performance degrades sufficiently. You're dealing with high voltages, which can be fairly dangerous. Service people who are not used to radar transmitters may even be scared of these things. They don't necessarily, not every service person wants to touch radar transmitters. So how about semiconductors? So traditionally it's been a very difficult problem to generate really high power at high frequencies. And it is still a very difficult problem, a fairly difficult problem at least. But there's been recent developments. And the main change that has happened is the development of gallium nitride transistors. It has significantly expanded the power available from semiconductor devices at these frequencies. And especially gallium nitride transistors grown on silicon carbide substrate. They can have very high power densities. Silicon carbide is a good conductor of heat. And the interesting thing is that there might be even next step after this. Diamond is even better conductor of heat. There's already companies producing these transistors on diamond substrate. Still very expensive. And from these transistors, there's a number of companies producing solid-state power amplifiers for radio frequencies. They have typically parallel gallium nitride transistors internally. You can combine also this kind of amplifier bricks externally to get higher power. Looking at the typical characteristics, the peak powers are still much lower than what we can achieve with these vacuum electron devices, klystrons and magnetrons. But the maximum pulse length is not around 1 microsecond. We can typically get 100 microseconds. And the maximum duty cycle up to 10% instead of 1 per mil. So here's the difference. And these kind of amplifiers are already available from a number of suppliers, mainly for the X-band, because there's quite a lot of different radars operating in the X-band, whereas C and S-band is still, they are not that generally available. So in weather radars, you need to transmit these long pulses to be able to achieve similar average power, similar sensitivity. And that leads to poor resolution and causes a blind zone close to the radar. And often you need to combine the outputs of several amplifiers to achieve reasonable or high enough power. That adds to the complexity, but it also gives redundancy. If you have several amplifiers, one fails, there are still others operating, you get some useful power out. There's a potential also for lower life cycle cost. So solid state devices don't have a defined lifetime, basically. So currently, solid state transmitters are used in weather radars, in some research radars certainly, operationally in Japan. And more X-band weather radars are brought into the market with solid state transmitters, because the power required in the X-band radar is smaller. So I mentioned this poor range resolution and the blind zone. There's techniques available to get around that problem, so-called pulse compression, and also a method to send the long pulse and additional short pulse to cover the close range, the so-called blind zone. So more complex driving of the radar, and you make basically two separate measurements, and you need to combine the results in the software. So this is the short pulse. You can measure close to the radar. Well, this is the long pulse, but the receiver is saturated close to the radar for a fairly long time. So you need to be combining these two different measurements in the software to get useful results throughout the range of the weather radar. So finally, Vaisala is currently developing a fully modern X-band weather radar, actually, using solid-state transmitter technology. We believe that it is the future. It's going to be a dual polarization radar, high performance. It's not going to be a very small portable unit. It's going to be a bit bigger because you need some size of antenna to get good performance. So this is for meteorological users and also for airport use. These are the customers we have in our mind when we're developing this. So this is a kind of a preview of things to come. Finally, so what is the future then? So these gallium nitride semiconductors are becoming more common. There's more manufacturers coming to the market. I believe that the cost is going to go down. They are still fairly expensive. There's not a big number of manufacturers, but more manufacturers are coming to the market. And there's this future path as well, gallium nitride on diamond, for instance. And as we see it, there are not too many companies still investing in this electron tube technology. Maybe their volumes are decreasing because this solid state thing is gaining ground in various radar applications. There's probably pressure to increase prices. If the volumes go down, you need to maintain a lot of competencies to be able to produce those devices. If the volumes go down, prices go up. And at the moment, today, comparable solid-state transmitters for weather radars already match or beat klystron transmitters in price. Magnetron transmitters are still the lowest cost and perfectly usable, perfectly fine in weather radars. So this is the status today. But what about the future? I believe this might be what happens in the future. although I will probably be retired before magnetrons disappear from weather radars. That's my guess. Thank you.